we're starting our unit on atomic structure, but before we really get into this, we just want to mention that there are some elements that you need to remember. There's, I don't know, 50-ish maybe, common symbols and names that you need to know. And then also mentioning that there are these guys that are listed on this sheet here, that there are 7 that are considered diatomic elements, and you need to understand that they do not exist by themselves in nature. They always buddy up with somebody else, with another atom of that same element. So for example, I've got listed here kind of in the order of where you would see it on the periodic table. So if you go over to the periodic table and look way over there on the far right, you see starting with iodine down there, and I'm going to say different names. What I'm going to do is call them by, I'm going to use a little phrase that might help you to remember it, but this is how they're seen on the periodic table. We remember, I bring clay for our new house, and that might help you guys remember what those 7 are, plus they're listed pretty closely together. If you remember those, when you write those down, the symbol for hydrogen would be H2, for example. Nitrogen would be N2, and so on. So those do not exist by themselves. For that reason, we call them diatomic, 2 atoms, just like it sounds. They exist with a partner. And this is really just saying the same thing. You need to write them as with subscript 2's on them. And then this last little phrase that I have down here, this is really going to come into play more when we start naming compounds. This is when people really start making this mistake. But remember, we only worry about them being diatomic when we're talking about them in their elemental state. If they're combined with something else to form a compound, it doesn't matter that they're diatomic. So for example, carbon monoxide. Yeah, oxygen happens to be diatomic when it's elemental oxygen. It's written as O2. But if it's carbon monoxide, this is the chemical formula for carbon monoxide. I don't care that oxygen is diatomic in its elemental state. So CO is the formula that would be written. That really, again, comes to be an issue when we start writing chemical formulas, which is many units from now. Okay, so with that information, we now jump into the new material, and what we're going to start talking about is atomic structure. You guys have seen bits and pieces of this throughout your science life at some point, but we want to think about how the atom is broken down in those subatomic particles. What we see right here on this screen is really, it's a 2-dimensional drawing of an atom, which is kind of hard to depict, but what we're showing is something known as like a Bohr's atom, is how you might hear that phrase. We can see that we have this nucleus in here that has the protons and the neutrons, and then we've also got the electrons outside of the nucleus, and there's different ways that we could phrase that. We could call it just outside the nucleus, orbits, energy levels, electron clouds, but we see that they're outside of that nucleus. The information that I have here, the numbers, the only reason I listed that is so that you could see we're talking about really, 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 really tiny, tiny things. So those are not numbers for you guys to learn or memorize. Okay, and I'm going to rush through this because we'll write it down on our paper here in just a second, but when talking about these subatomic particles, it's kind of hard for us to talk in terms of masses unless we create some sort of relative scale, some sort of relative mass scale. And what we're going to see is that carbon-12 ends up being our relative mass that is used for that. So we're going to eventually write down on our paper that an atomic mass unit is equal to 1/12 of a carbon-12 atom. That's what ends up being used as our standard. So knowing that carbon-12 is our standard. This diagram below is just trying to illustrate that by getting a standard like that, we can then compare masses of all of these different isotopes or all of these different atoms by, for example, here we're showing that 32 atoms of hydrogen would have it has a relative mass of 32. So it's giving us a way of comparing these things by having a relative mass. So now putting that into useful terms for you guys, this is what you've got on your paper here. If we want to look at our 3 subatomic particles, the proton, neutron, and electron, we can start off by writing down the symbols. And I know you guys all know the symbols for this. What's the symbol for a proton? P. And what's the charge of a proton? Positive. So quite often a better way to even write that symbol is as a P with a little plus on top. And then neutrons are lowercase. These are lowercase letters. I know that P is hard to tell. But the neutron is a lowercase n. What's the charge of a neutron? What is it? Nothing. That's right. 0. So there is no charge on a neutron. It is neutral. And then finally, an electron has a negative charge. So that's the first thing that we really need to make sure becomes really quick, easy knowledge for us, that we know that information. Now, if we want to think about the mass of these particles, remember we want to come up with some sort of relative mass, and that's what we're going to do here with something known as the atomic mass unit. So under mass, let's go ahead and write that in, because it really would not be very useful for me to talk in terms of how many grams a proton weighs, or an electron or something like that. The grams would not be very meaningful for us. So we come up with a standard, and that standard, like we said, was based on the carbon-12 atom. So we're going to rephrase this. Here we're going to say that 1 AMU, and you might want to write this down, equals 1/12 of a carbon 12 atom or isotope, so we'll just write that. It is 1/12 of a carbon 12 atom. Okay? So given that, and what we know about what we're going to learn about these mass numbers, that will make more sense. Just 1/12 of that is going to be an AMU, is what the reference was. So I know you guys have learned this at some point. How many AMU are in a proton? Does a proton have? Just one. So the proton is 1 atomic mass unit. Happens to be the same as a neutron, which is 1. And then I just heard, thinking about the electron. The electron, is it heavier or is it lighter? Lighter. How light? 1/2000th, which I've always written it as 1/1836th, somewhere around that. But you know what? Who really cares? Because what we get from that is that it is so small that we're pretty much going to say, hey, that's equal to 0. The electron, comparatively, does not have a mass when compared with the proton and the neutron. So protons and neutrons have 1 AMU for a mass. The electron is right around 0. It's so small. And then if we want to think about how this whole atom is structured, where do we see the mass of our atom? Well, it's in the proton and the neutron. Where are the protons and the neutrons located? In the nucleus. Whereas the electrons are not in the nucleus. And again, there's so many different ways to phrase this. I'm just going to say outside of nucleus is where you see those electrons. You could write energy levels or clouds or orbits. Okay, so that's what we see here, is that our relative mass unit is based on carbon-12, so 1 AMU equals 1/12 of a carbon-12 atom. And then we move on to some terminology here. Oh wait, I'm sorry, not yet. This is just to give us a perspective of how small we're talking about with an atom and the different subatomic particles. So if you had an atom that was the size of this stadium, then the nucleus would be about the size of a marble. So it'd be really tiny comparatively. Another example, and I like this one, think about an atom being a bale of hay. And this bale of hay weighs 500 pounds. So you've got this bale of hay weighing 500 pounds. That's your atom. The nucleus of that atom would be the size of a speck of pepper, and it would have a mass of 499 and some odd pounds. So all of that mass inside of that tiny speck of pepper, and the rest of it is just empty space. So that's a really dense nucleus that we're talking about. Which brings up this part. How big is an atom? Well, if people were the size of atoms, the population of the world would fit on the head of a pin. And an atom weighs about, I don't even know how to say that, one very small fraction of a pound. And if we're talking about the empty space in an atom, if you were to remove all of the space in atoms of a 200-pound man, then he would be about the size of a particle of dust. So lots of empty space, just a really dense nucleus. Okay, so now in order to go further, we want to make sure we understand some terms. As far as these abbreviations go, you should know this. If I have the abbreviation of Z, you should know that that means atomic number, and the abbreviation of A means mass number. To help you remember this, I don't know if anybody in here is in German, but in German, and you don't need to know this, I'm just trying to help you remember this. This Z comes from Zahl, which is a German word that means number. So that was coined, this whole, the abbreviation was coined before we really thought about mass numbers, back when it was just considered about the atomic number. So think about the periodic table, 1, 2, 3, 4, 5, you know, the consecutive numbers there. That's what this is based on, those numbers. So that's where the Z comes from. The mass number came about later on. So let's go back to atomic number. What is the atomic number? It's equal to the number of, say it again, protons. Number of protons. It is what defines that element. If I say, hey, I've got an atom here that has 6 protons, there's no doubt the only possibility is it's got to be carbon. So the number of protons defines what the element is, and that's your atomic number. Then we move down to mass number. Mass number, where did we say the mass was contained in an atom? In the nucleus. Hey, what's in the nucleus? Those protons and neutrons. So that's it, you just add them together. Your mass number is your number of protons plus neutrons. Well, protons are whole numbers, neutrons are whole numbers, therefore protons plus neutrons would equal a whole number. It would not be a fraction of a number, which if you happen to look at periodic table right now, you see on your periodic table, the one that I have in class has these red numbers that have fractions to them. Those are not, I say fractions, they're decimals. But those are not whole numbers, so therefore those are not mass numbers. Instead, mass numbers are going to be the whole number, so therefore it is not on the periodic table. We do not see mass numbers on the periodic table. It's the number of particles in the nucleus, but it's not written on your periodic table. Okay, so now what we can do is we can look at creating some nuclide symbols based on this information, based on your mass numbers and your atomic numbers, and even the charges, because we know that there's a difference in charge. You've got protons and you've got electrons, positives, negatives. So we can figure out some information about this. What a nuclide symbol is, it's just a way of representing that information. So in the middle is the element symbol, whatever it happens to be. So for example, over here to the right, I have the element of magnesium that is written down. So you have your element symbol in the middle. Remember, A stands for mass number, and Z stands for atomic number. So when writing these, usually you will see a large number over a small number. It will never be the other way around. It could be the same, but it'll never be, you could have the same number on the top and bottom, but it'll never be a larger number on the bottom. It'll always be the larger number on the top. Okay, so you've got your mass number over your atomic number, and then the charge would be written in the upper right-hand corner. So another way of writing what you see here with magnesium is you might see a 0, which would show that it has 0 charge. If you don't see a 0, then it's just assumed that there's no charge to it. Now, this is considered the nuclide symbol, but earlier when we talked about carbon-12, I wrote it a little differently. Instead, I just wrote the word carbon. So you can write the element name, and then when I wrote 12 out here, what was that? Or for example, here with our magnesium, what is this 26 equal to? The mass number. So that's another way that you might see it represented sometimes. Now, if you see the word magnesium and you have a periodic table, you know that magnesium would have to have an atomic number of 12. So that's not going to change. That tells us essentially the same information. Okay, so you do not have a place for this on your notes. What you need to do, I think over in the left-hand column, you can probably turn your paper and just write it down real quick. It's a quick, easy definition. But you should know this term. Ions, all they are charged atoms. Ions are charged atoms. Well, in order for an atom to get charged, what do you think has to happen? Any ideas? What do you think? Okay, so you have more protons than electrons or more electrons than protons. In order for that to happen, where do you think the change happens? You have to lose an electron or gain an electron. You can't gain or lose protons. That's the key from this, is you can't gain or lose protons, because then it's no longer the same element. So what I would do if I were taking notes on this, I would probably just make myself a note like the atom gains or loses electrons. There's your nice abbreviation for electrons. Gains or loses electrons. It's not possible to gain or lose protons. That's called nuclear changes, nuclear reactions. That's something we get to in our very last unit of the year, but that's not going to be what happens in chemical reactions. Okay, so now that we understand ions are charged atoms, they get charged by gaining or losing electrons, we can look at some different nuclide symbols. You don't have these two examples on your sheet, but that's okay. You have plenty of examples after that. We're going to kind of play around with this and fill this in class. I'm going to let everybody here do it. So we will pause and you will see the answers. There are some really smart people in this class and they just whipped this out really quickly. Nice job. Okay, now we move on to this table that you guys have on your homework sheet, or not homework, your notes. And we're going to go ahead and fill this in as well. And bear with us at home because I've got people that are going to be doing this again in class. So this first one, we're looking at this. I see this Ne. We're also given mass numbers. And we are going to figure out our atomic number based on this, knowing that we can look at a periodic table. At all times, we could look at a periodic table. So knowing that it's Ne, okay, what's it going to be? And he's looking at neon on the periodic table, and he's trying to come up with atomic number for neon. 10! It is 10. You got it. Okay, so 10 for our atomic number. We know that there's a mass number of 22, and we want to figure out our number of protons. Might relate, might not. Nina, what do you think? Nina, sorry. It would be 10 because we know our atomic number and our number of protons are always going to be the same. We're given that there's 10 electrons, and then we want to figure out our number of neutrons. 12. And we got that by saying that we have our mass number of 22 minus our number of protons. So it was the protons plus neutrons minus just the protons gives us the neutrons. Okay, we are going to do this, I think, on the side, and then we'll come back. Okay, we are back, so pause this if you need to and double check your answers. Some things to keep in mind. Charges, remember, are based on your protons and your electrons, so that's how we came up with these answers right here. And then, again, in order to find this information, you would have to have a periodic table in front of you. Okay, now that brings us to something known as isotopes. I've used that in conversation a little bit, but I haven't really given it a name. So now is a good time to give this a name. Isotopes are just going to be when you have atoms of the same element that have different numbers of neutrons. So atoms of the same element with different numbers of neutrons. Atoms of the same element with different numbers of neutrons. Hey, if they have different numbers of neutrons, what else is different? Their masses, yes. So, therefore, different mass numbers. So if they have different numbers of neutrons, they would have different mass numbers. But notice it does say that they are atoms of the same element. So what subatomic particle has to be the same? Protons. Okay, so those are what isotopes are. In this example, do not worry about these fancy little names that we have down here. This just happens to be something that has some very, very common isotopes, and therefore they're given some names that are commonly used, but don't worry about those. You don't have to learn that. But this is an example where hydrogen, there are 3 common isotopes of hydrogen. We know it's hydrogen because in all cases, it's got 1 for an atomic number. But what changes is the mass number. In this first example of hydrogen 1, and remember you could write that hydrogen 1, this could be hydrogen 2, this could be hydrogen 3. In hydrogen 1, how many neutrons are there? 0, because you've got a mass number of 1 and an atomic number of 1. That mass number is entirely based on that 1 proton that it has. It doesn't have any neutrons. Here we've got 1 neutron, here we've got 2 neutrons. Okay, so those are examples of isotopes. Here's another isotope example for you. If we've got lithium, well, I know lithium has an atomic number of 3. It has 3 protons. So all of these have 3 protons in the examples, but they have different numbers of neutrons, therefore their masses are different. You've got 6, 7, and 8 for the masses. Which brings us to the fact that on your periodic table, we said this earlier, you don't see any of these on your periodic table. Instead, this is what you see on your periodic table. This is what we're going to learn about tomorrow. But just to cut the suspense a little bit for you, this number right here, you should see that it's kind of similar to these guys. What it is it's a weighted average of all of the isotopes of that element. So that what we need to do is figure out, if we know the percent abundance, which that's been discovered experimentally, we know the percent abundances of those different isotopes, then that's how this atomic mass is calculated. So that's what you see on your periodic table. And then, let's see what else we've got. Okay, so now I think this is the end here. It says you try. It doesn't tell you what to try though. Let's, what you're going to do is write nuclide symbols for this. And what we're looking at is carbon 12 and carbon 13. How would you write the nuclide symbols for carbon 12 and carbon 13? Well, carbon is a big capital C. If it's carbon 280, not that there's such a thing, what goes right down here? 6. It is carbon, so there is a 6 that goes down there. Doesn't matter what isotope of carbon it is, a 6 goes down there. Well, this is carbon 12. What number goes up top? 12. If I asked how many neutrons there are, the answer would be 6, because you would subtract those. So the mass goes up top, and the number goes on the bottom. Let me erase my little things here. And then finally, it happens to be a neutral atom of carbon. There's no charge to it. You just have to assume there's no charge unless you're given some information to tell you otherwise, that it's forming an ion. But here we're not seeing that it's an ion. So in this case, we are going to say it has a charge of 0. If you don't see that 0 in there, then it's just assumed. Okay, carbon 13, what number is going to be the same as over here on the left? 6. And then what's the other one? 13 goes up top. That's it. That is all. Nice job. Let's see here.